All right, everyone, let's get started. Okay, we'll continue for chapter 5. Today we try to finish chapter 5. Again, chapter 5 is all about confidence intervals. Okay, so far we have discussed 1, 2, 3, 4 different situations. Okay. For example, confidence interval for large sample population mean, okay, or for proportions, a small sample confidence interval for population mean, and confidence interval for difference between two means. Okay, and this section 5.5, will be confidence interval for difference between two proportions. Okay, so you will see the equation almost the same. Okay. The procedure is the same. Okay. Just depending on what the question is asked, you choose the right set of formula. Okay, so look at the setup. X, number of success in n X independent Bernoulli trial. Okay. Success probability Px. Okay, so please mute yourself if you haven't done so. Okay, unless you have a question. Y is number of success in ny independent Bernoulli trial with py success probability. Okay, and X follow bin binomial nx px, y follow binomial ny py. Okay, and similar to a situation in section 5.2, which is confidence interval for proportions. Okay, we also modify the nx and ny. Okay, so modified nx is nx plus 2. Modified ny is ny plus 2. Okay, and also we have modified px and modified py. Okay, so same as section 5.2. And here is the formula for 100 times 1 minus alpha percent confidence interval for difference between two proportion, px and py. Okay. Because for proportion, the value is between 0 and 1. Okay, so there's a lower limit for the difference between two proportion. Okay, so the low portion will be minus 1. Okay, when px minus py is like a 0 minus 1, so we have minus 1. Okay, so the confidence interval for the difference between two proportion cannot be lower than minus 1. Okay, so the lower limit will be minus 1. And upper limit cannot be larger than 1. Okay, because 1 minus 0, the extreme case, the upper limit will be 1. Okay, so if it is turned out to be larger than 1, it's not correct. So replace with 1. Okay. Okay. And also, this is the more advanced method, more accurate method. That's a traditional confidence interval. Okay, but we will not discuss that equation here. Okay. Just use this formula for difference between two proportions. And then let's do an example together. Okay. So as I said, try to look at the last sentence to figure out what the question is asking, and you can zoom in what set of equation to use. Okay, here. So 95% confidence interval. Okay, and you know this is chapter 5. And then difference between success rate. Okay, so for success rate, this is proportion. So confidence interval for difference between two proportion, you will use the equation from section 5.5, which is here. All right. Then let's read the question together. So method to estimate strength and stiffness requirements should be conservative in that they should overestimate rather than underestimate. Okay, so that's true. The success rate of such a method can be measured by probability of overestimate. Okay, there's a paper present the result in an experiment that evaluate a standard method for estimating the brace force for compression web brace. Okay, so this is one of the structural member. In a sample of 380 short test column, okay, the method overestimates 304 of them. In another sample of 394 long test column, okay, the method overestimates the difference, the force for 360 of them. Okay, so it asks for the difference between these two proportions. Okay, so let's set up the equation for nx and ny. Okay, so let's define nx. Okay, is for the short test column. Nx is 380, so we have 380 samples. Okay, and the modified nx will be nx plus 2, as shown in this equation here. Okay, so nx plus 2. So 382, and px, use the equation, okay, is 304 plus 1 over 382. Okay, so that is based on that equation. Okay, x plus 1 over modified nx. And same thing for y. So modified px is this much. Okay. And same thing for y. Let me just write down. Ny, modified ny. Okay. And modified py. All right. Okay, and then we use the confidence interval equation, this one. Okay, so plug in the number into this equation. So modified py minus px plus minus z half alpha. Okay, so this is the z value. And for z half alpha, let's figure out z half alpha first, because this is 95% confidence interval, and z half alpha from the z table will be 1.96. Okay. Again, I will not go to the z table. Okay. So you should be able to figure out that yourself in this step. So modify py px modify nx. Okay. All right. Then we can just plug in a number. Modify py is 0.91116 minus modify px is this much. Okay. Plus minus z half alpha is 1.96. Okay. Square root. Okay. Then you can just plug in modify px, modify nx, which is here, and here. Okay, so I will just skip the details. Okay, so this is the final answer for 95% confidence interval. Okay. Next session, small sample confidence interval for difference between two means. Okay. We also have an early section talk about difference between two means, okay, which is section 5.4. So that is for large sample. For small sample, we'll use t value, student's t table, okay, not a z value. Remaining will be the same. Okay, so let's look at this. For small sample, x1, x2, xnx, okay, that's the actual requirement for small sample. It has to be following normal population. Okay, so this is actual requirement when the sample size is small. Okay, and also for y should be also follow normal distribution. And also these two samples should be independent to each other. Okay. Depending on whether these two population has the same variance or not, okay. So if the two population does not have the same variance, okay, we should use equation here. Okay, for 100 times 1 minus alpha percent CI, okay, for the difference between the two means, we use this equation. Okay, as you can imagine, we use student's t value. Okay, for t value, we have two parameters. Okay, degree of freedom and also depending on the confidence interval, we have the half alpha. The degree of freedom, the equation for that is here. Okay, so V is the number of degree of freedom is given by this equation. Okay, so if this equation give you not integer, you should round it up to the nearest integer. Okay, half alpha is the same. Okay, for x, this is the sample standard deviation for x. Sy is sample standard deviation for y. Nx and ny is the sample size. Okay, and this is the sample mean for x and y. Okay, so this is the equation for small sample confidence interval for the difference between two mean values. And here is the example for that. Again, look at the last sentence. Okay, 98% confidence interval. This is difference in mean. Okay, so difference between two means. Okay, then depending on the sample size, it is large sample or small sample. Okay, if it's a large sample, we should use the equation from the early section, which is section 5.4. If the sample size is small, we should use the equation here. Okay, and let's read the question together. So reason-based composite used in restorative dentistry. Okay. Another paper present comparison of the surface hardness of specimen cured for 40 seconds, okay, with constant power with that of the specimen cured for 40 seconds with exponentially increasing power. Okay, all right. First, we have 15 specimen. Okay, 15 is less than 30. This is small sample. Okay, small sample. 15 specimen cured for with each method. So the those cured with constant power had average surface hardness of 400.9, standard deviation of 10.6, Cued with another method, which is exponentially increasing power, had another surface hardness and another standard deviation. Okay, we know this is small sample. Okay, and also we notice the difference between two means. So we can zoom in this equation. Okay. First of all, let's figure out the parameters we need. For the sample mean, it's given by the question, 409. For the sample standard deviation for one of the methods, 10.6. The sample size, 15. Okay. This is all given by the question. For y, we just copy that number down here. Okay, then to use the degree of freedom, okay, V is the degree of freedom, and the equation for V is here. Okay, we just need to plug in the number of Sx, Nx, Sy, and Y. Okay, turned out the degree of freedom is around 22. Okay, to the nearest integer, about 22. So t value will be 22 for the degree of freedom. Okay, and alpha is based on the level of confidence interval. Okay, for 98% confidence interval, the half alpha. Okay, so half alpha. Okay, 98 equal to 100 times 1 minus alpha. So turned out alpha is equal to 0.02. So half alpha will be 0.01. Okay, so the t value will be 22, 0.01. Okay. Let's look at the t table. So the t table will be here, table 8.3. For the degree of freedom of 22, which is here, okay. And alpha 0.0, half alpha is 0.01. Okay. So 0.01 is here. So it turned out the t value will be here, 2.508. Okay. So t half alpha is 2.508. And then let's plug in the 95% equation, 98%, sorry. Right. Okay. So for sample mean, 400.9. For y is 367.2 plus minus. The t value is 2.508. Okay. Sx 10.6 square nx 15. Sy 6.1 square, Sy 15. Okay. Then you can just figure out the confidence interval for that. Okay. Probably you can feel chapter 5 is pretty straightforward. Okay. Just need to figure out what set of equation to use, and then the remaining will be very straightforward. We either use the z table or the t table. Okay. Okay. For this, okay. So for the two population, when they do not have the same variance, we use this equation. Okay. Sometimes they have the same variance. Okay. If they have the same variance, we should use another set of equation. Okay. So this is a special situation when the two population has equal variance. Okay. If they have the equal variance, we still use t-value. Okay. But for the t-value, the degree of freedom is nx minus ny plus ny minus 2. Okay. And then it's still half alpha. Okay. And also we have a quantity called SP. Okay. SP is called put standard deviation, which is given by this equation. Okay. So SP is a function of nx, sx, and y as y. Okay. So again, when we know the two population has the same variance, that's a special situation. If that's the case, we should use this equation. Okay. And the next example shows us when the two population has the same variance. Okay. First of all, last sentence. 99% confidence interval for difference between two means. Okay. And then let's look at the sample size. The sample of 10 bottles. Okay. And we know this is a small sample. For small sample, we should use section 5.6. Okay. But the question tells us, okay, so it is believed that moving the machine may have changed the mean field volume, but is unlikely to change the standard deviation. Okay, so unlikely to change the standard deviation. That means the standard deviation does not change. Okay, so let's read the question. Machine is used to fill plastic bottle with bleach. Okay, so we have a sample of 18 bottles, has a mean of this, standard deviation of that. Okay. And then the machine moved to another location. We have another sample of 10 bottles, okay, with a new mean and a new sample standard deviation. Okay, so the question is asking for the confidence interval for the difference between two means. This is a small sample, but the special situation here is they have the same standard deviation. Okay, that tells us we should use this equation. Okay. So we need to figure out what is SP. Okay. The mean value, first we copy whatever the question tells us. Okay. So because they have the same sigma, same population standard deviation, so we use the equation here. So we calculate the SP. Okay. So SP is based on that complicated equation here, this one. Okay. But just plug in the number for nx, sx, and 1 and sy, okay, which the question already tells us. Okay. So we calculate SP. Okay. And for the degree of freedom, so that is nx plus ny minus 2. Okay. Because here, this is degree of freedom, nx plus ny minus 2. So nx plus ny minus 2. So that's 26 degree of freedom. So the t-value will be t26 alpha, half alpha will be 0.005. Okay, so for 99% confidence interval, alpha alpha will be 0.005. Okay, again, go back to table 8.3. Okay, here, the degree of freedom is 26. 26 here. Alpha alpha is 0.005 here, right? For 0.005 half alpha, 2.779. Okay. Sorry. Here. It's here. So 2.779 for the t-value. And then for 99% confidence interval, we use that equation. Okay. SP is and then you plot the mean value for x and y, you get a final answer. Yeah. Okay. So use this equation. Okay. So here tells us we do not assume the population variance are equal unless the question clearly tells us that's the case. Okay. Sometimes even when the sample variance are nearly equal, but we can still not conclude that the population variance are also equal. Okay, because this is a small sample. Even though the sample variance may be equal, but the population variance may not be equal. Okay, so the solution is we always assume the variance are not equal unless it is quite certain that they are equal. Okay, so unless the question tells us the two sigmas are actually equal. Okay, so in this section, we discussed two cases. When the variance are equal, we use this set of equation. In the general case, if we do not know the variance are equal, we use this equation instead. Okay. So that is section 5.6. And we're almost there. We have 7 different cases for confidence interval. And the next one is the last situation, paired delta. Okay, so what is paired delta, first of all? Okay, in some cases, we may wish to design experiment that each item in one sample is paired with an item in another. Okay, so in this situation, the sample are no longer independent. Okay, let me give you an example. Okay, so I'm doing research on concrete, so I always give you an example in concrete. Okay, so let's say we have 3 concrete samples. Okay, and for each sample, we measure the density of the sample, and we also measure, let's say, the strength of the sample. Okay, so for each sample, 1, 2, 3, we measure the density and strength. So this is one pair data. Okay, so this is one example of pair data. So here's another example of pair data. So we have a tire manufacturer want to compare the treadwear of tires made of two materials, the new materials and the conventional materials. Okay. And one tire on each type is placed on each front wheel of each of the 10 front wheel drive automobiles. Okay, so for 10 cars, one wheel is made by, the tire of one wheel is by new materials. Another wheel on that car is made by conventional materials. Okay, and each car will run 40,000 miles and then compare the depths of tread, how much consumed. So this is a pair data. Okay, so this is one pair data. So car number 1, this is tread depths. The cross is the tread depths for new materials, and the circle is the tread depths for old materials. Okay, and this is the result for all the 10 cars. And we can see for most of the case, most of the car, the new materials has deeper tread depths. Okay, which means the new materials is better. Okay, but not for car number 8. So this is another example of paired data. The setup. Okay, so define x1, y1. So this is one pair data. Xn, yn, okay, is another sample pair. Okay. And di is the difference between xi and yi. Mu x and mu y population mean for x and y. Okay. So here we care about the confidence interval for the difference between mu x and mu y. Okay. Because d is equal to x minus y, okay, then the mu d will be equal to mu x minus mu y. Okay. Here's the equation. D1, Dn is small random sample. Okay, small random sample of difference of pairs. For this level of confidence interval, we should use this equation. As we can see, we use t value. This is the small sample, so we use t value. The degree of freedom is n minus 1, then half alpha. And this is SD is the sample standard deviation of the sample size n. Okay. And when the sample size is large, okay, then we use the z value, and we use this equation. Okay. So for pair data, depending on the sample size, we use either this or that. Okay. And the sigma d is the standard deviation for d. Okay. And if we do not know that, we can use the sample standard deviation over square root of sample size n. Okay. So that is pair data. Depending on the sample size, we use either the t value or the z value, one of these two equations. Like in this sample, again, look at the last equation, sentence, 90% confidence interval for the mean reduction in systolic blood. Okay, so what's that? Let's read the question. A group of 5 individuals, so that's small sample, okay, with high blood pressure were given a new drug that was designed to lower the blood pressure systolic blood pressure was measured before and after the drug. Okay, the result shown here. So for each individual, okay, so this is before and after. Okay, we will see a table, and you know this is the paired data. Okay. And because this is a small sample, for small sample, we should use this equation. We use the t-value. Then let's just calculate the parameters here, one by one. For example, the mean value for difference, okay, the difference is here. Okay, we just add all the difference together. So 25 plus 32 plus 39 plus 23 plus 38 divided by 5. Okay, so the mean value for the D, we calculate that. And also the standard deviation for the D, and we can also calculate that. So this is the equation we learned from chapter 2. Sample size is 5, so it's 5 minus 1. Okay. So square root for each one of these D, so we can calculate that. 25 square plus 32 square plus 38 square minus n. Okay, mean value is, so n is 5, the mean value is 31.4 square. Okay, so we can calculate the standard deviation, sample standard deviation. This much. For the t-value, the degree of freedom is n minus 1 and half alpha. Okay, so n minus 1, n is 5. We have 5 sample, so that's 4. Half alpha for 90%. Okay, confidence interval. So for 90%, the half alpha will be 0.05. Okay, and then for degree of freedom of 4, 0.05 is here, 2.132. 2.132. Okay. And then we just plug in the numbers into this equation. Okay. 2.132 SD 7.3 0 and 5. Okay. All right. Okay. So that's the end for section 5.7. Okay. From 5.1 to 5.7, we discussed all about confidence interval. Okay. Depending on, for example, the sample size, large or small, or questions for asking for population mean, or difference between two means, or proportion, or difference between two proportions. Okay, and pair data also. Okay, so the equation are pretty much similar. I just suggest you to write down the equation side by side, so you can select easily what equation to use depending on the questions, what the question is asking. Okay. The last section for chapter 5 is 5.9. Okay, so 5.8, we just skip that. Okay, we do not discuss 5.8. So last section is 5.9 and also 5.10, which is we doesn't have any calculation for that section, which is simulation. Okay, so 5.9 is another two type of intervals. One is called prediction interval, another one is called tolerance levels. Okay, so first of all, let's look at what are prediction intervals and the tolerance levels. Okay, so we know confidence interval for parameters such as population mean, or proportion, or difference between two means. Okay, so we calculate the interval depending on what level of confidence interval, okay, that likely to contain the true value of the parameter. For example, the population mean. Okay. So prediction and tolerance interval are concerned with population itself and with value that may be sampled in the future. Okay. And the following equation we're going to discuss in this section only valid when the population is normal. Okay, so this is a big condition. So only when the population is normal, then we can use the following equation in this section. First of all, prediction interval. So prediction interval is defined as an interval that is likely to contain a value of item sampled from a population in the future. Okay. And here's the equation. X1, X2, Xn are sampled from a normal population. So this is a big condition. Okay. And Y is another item to be samples. Okay, this is in the future. Okay, to be sampled from this population whose value hasn't been observed because this is from future time. Then 100 times 1 minus alpha % prediction interval for Y is this. Okay, again, pretty similar to confidence interval, as you can remember, but with a little bit difference. Okay. So the probability here, you should use probability, is 1 minus alpha that the value of Y, which is the future value, will be contained in that prediction interval. Okay. And we use the t value, degree of alpha, degree of freedom is n minus 1, and half alpha. Okay. And the S is the sample standard deviation. Okay. Here is one example. So 95% prediction interval, okay, also coming from chapter 5, for the strength of block whose strength has yet to be measured. So that's for a future value. Okay. So we have a sample of 10 concrete blocks manufactured by a certain process, has a mean compressive strength of 1312 megapascal. Okay, so this is not a realistic value. Okay. For normal concrete, the strength is around 30 megapascal in compression. More than 100 megapascal is called high strength concrete. 1300 megapascal is unheard of. Okay, but anyhow, we calculate 95% prediction interval. Figure out the t-value. First of all, depending on the 95% prediction interval, we figure out alpha and half alpha. So half alpha is 0.025. Okay, so the t-value. Okay. So n is sample size is 10. So t 10 minus 1, half alpha 0.025. So n minus 1 is 9. The degree of freedom is 9. 0.025 is here. Okay. So 2.262. Okay. So again, it's from table 8.3. Okay. So plug in the equation here. The mean value plus minus the t value, 2.262 s 1 plus. So the mean value is given by the question here. S standard deviation is here 25. N is 10. Okay. So 95% prediction interval for the strength of the block will be between 1253 and 1371 megapascal. Okay. Look at the difference between prediction interval and confidence interval. Okay. We know prediction interval is for future values. Okay. But look at interval itself. We can see the only difference between these two intervals is the one here. Okay. The one here, which actually increase the interval by quite a lot. Okay. So for prediction interval, we use plus minus s times square root of 1 plus 1 over n. Okay. But for confidence interval, we use 1 over n itself. Okay. So the difference is that one. So that will make the interval wider than its corresponding confidence interval. Actually, it is much wider. Okay, much wider. Okay, because 1 minus 1 over n is a small value. Okay, so 1 plus that value, so we make the interval much wider. So that is because prediction interval is for future values. We need to make the interval wider. Okay. We also have one-sided prediction interval, same as confidence interval. We have one-sided upper end and lower bound. Okay. For upper bound, okay, we use plus. Okay. T value is n minus 1, and then it is alpha. Okay, not half alpha. For lower bound, we use minus. Again, we use alpha and not half alpha. Okay. Almost the same as we did for one-sided confidence interval, if you remember. Again, for prediction interval, remember it has to follow a normal distribution. Tolerance interval. Okay, so tolerance interval is defined as an interval that is likely to contain a specific proportion of the population. For example, an interval contains 50% of the whole population. Okay. The condition also specify it has to follow a normal population. Okay, so this is important. And here is the equation for tolerance intervals. Okay. So x1, xn, a sample from a normal population. Okay. For tolerance interval, so here is 100 times 1 minus gamma percent. Okay, so this is the proportion of the population contained in that tolerance interval. Okay, we also have confidence level, which is 100 times 1 minus alpha percent. Okay, and we have new parameters called k. So k can be found from a new table 8.4. Okay, so for k it has 3 parameters, as we can see here, n, alpha, and gamma. Okay. So let's look at an example to see how we can calculate tolerance interval. Okay. So the length of boats manufactured by certain process are known to be normally distributed. So that condition is met. In a sample of 30 boats, the average length is 10.25 centimeter, standard deviation 0.2. Find a tolerance interval that include 90% of the length with 95% confidence. Okay, so 90% of the length, which is this, 95% confidence. Okay, we can figure out alpha here. Okay. So the key value n alpha gamma. Okay, so alpha gamma is here and here. N is the sample size. The sample size in this question is 30. Okay, so first of all, write down the sample mean, sample standard deviation. Okay. Then the key value n, alpha, and gamma. Okay. For n, it is 30. For alpha, okay, so alpha is here, depending on the confidence level. The confidence level is 95%. Okay, so the alpha will be 2.05. Okay, so 100 minus 95 is 5%. Okay, and the gamma, depending on the proportion of the boats increase, 90%. Okay, so gamma will be 100 minus 90%. So that is 0.1. 0.1. Okay. Then let's look at the key value, table 8.4. Okay, table 8.3 is students' T distribution. Table 8.2 is the Z table. Okay, here is table 8.4, that's the tolerance factor for normal distribution. Okay. The sample size is 30 here. Okay. It only shows two different confidence levels, 95% and 99%. So in our case, it is 95%. So it's in here, this column. And then percent of population content, that is 90%. So it's here. Okay, 2.1398. Sorry. All right, so that is 2.1398. So the tolerance interval will be okay. All right. So that is the tolerance level. Okay. So in this section 5.9, we discuss tolerance interval, okay, and also prediction interval. Okay. So that's the special situation. But the majority of this chapter, we discuss confidence interval. The last part is about how to use simulation to construct confidence interval. Okay, we can just read it together. Okay, so if x1 to xn are independent random variables with known standard deviation, okay, and u is a function of this different x. Okay. And then it is viewed normally, but not always. Then the U is also normally distributed. Okay, and we can use simulation to estimate its standard deviation. Okay. So we can use computer program, okay, to do the simulation. For example, we generate 1000x from a normal distribution. Okay, that is specify the x, and then we can transfer this x value into u value depending on the function. Okay, and then we can check the u value to see if this 1000 u value are normally distributed or not. Okay, so again, we can use computer to help us to use simulation to construct confidence interval. Okay, less than for chapter 5. Okay, so in chapter 5 we learned confidence interval for large sample and small sample, for mean value, a difference between mean value, for proportion, a difference between proportion, and for paradata. Okay, and lastly, we discussed the prediction interval and the tolerance interval, which is obviously not a focus for this chapter. Okay. Next class, we will do some practice section for chapter 5, and I will also assign our homework for chapter 5, and then we'll go to basically our last chapter for this class, which is chapter 6. In chapter 6, we discuss hypothesis testing. Okay, very similar to chapter 5. We do the hypothesis testing for different situations, such as mean value, proportion, difference between two means, difference between two proportions. Then, depending on the sample size, is large or small. Okay, that's it for today's class. Any questions? Okay, So if not, I'm going to see you Thursday next week. Thank you.